who will speak about bisections inspired by two of my favorite mathematicians.
Okay, so thank you very much, Jordan, for inviting me. Thank you to all of you for coming. It's great to have everybody here. As always with my talks, I encourage questions, comments. If I'm not making things clear, I'd rather not get through the end of everything and make things clear than rush through everything and have everybody be confused. So please don't hesitate to ask questions. As Doran indicated, this is going to be a talk that is inspired by a lot of, dare we say, ancient mathematics, at least ancient in some sense, that this is going to be inspired a lot by the work of two mathematicians. So Sylvester, back in the late 1800s, did a lot of work with partitions. And he was also followed by Major Percy MacMahon, who came up with a very interesting partition identity, among other things. And so basically the point of this talk is going to be looking at some new partition identities that are inspired by MacMahon's partition identity, and the methods that we're going to be using to prove them are going to be bijective methods, and those bijective methods are going to be making very heavy use of some work of Sylvester. So that is the setup for the talk. So anyways, without further ado, as every partition talk, I must define partitions in case you have not seen it before. And so just to show partitions, let's say 4, how many ways can we write 4 as the sum of positive integers where we don't care about order? So there are 4 ways to write 4. 5 ways to write 4. Let's get that count right. And so then there's lots of things that we can do with partitions. My favorite thing to do is to look for partition identities, which is when partitions into one type is equal to, for any given n, is equal to the number of partitions into a second type. And so one of the, probably about the most famous one, is Euler's odd distinct theorem, which says the number of partitions of n when you only use odd parts. So in this case, odd is 3 plus 1 and 1 plus 1 plus 1 plus 1. So there's 2 ways to write 4 only using odd parts. So this is the same number of ways to write it in distinct parts, where we don't repeat any parts whatsoever, which is just 4 and 3 plus 1. So there's 2 ways here, 2 ways here. Euler's theorem tells us that those 2 numbers will always agree, no matter what number you start here. And so, there's lots of ways to prove Euler's theorem. This is probably the generating function proof might be my single favorite proof in all of math, just because of how slick it is. You do no work whatsoever, it feels, and then you end up proving the theorem. But this is, as I alluded to before, this is a talk about bijections. And so we want to think about how to prove this bijectively. And so the main bijective proof, the one that most people think of when they think of a bijective proof of Euler, if you've only seen one bijective proof of Euler before, you've probably seen Glacier's bijection. And that is one where you basically just chop parts in half or glue duplicates together and stuff like that. That's not the one I'm going to be talking about today, because as it turns out, there's a different bijection that is due to Sylvester that has some very desirable properties. And so I'm going to be using Sylvester's bijection to prove some new partition identities bijectively. And it will turn out Sylvester's bijection has a very important property that will be a key ingredient in the proof. So as for Sylvester's bijection, and so this is going to be a case in which I'm going to go through this at a high level. I'm just going to basically just show an example or two and say, okay, you can see what the bijection is doing. I'm not going to worry about proving it is a bijection. I'm going to show one direction of the map and say, verify the details for yourself to see that it is in fact a bijection. And the way that we're going to be doing this is we're going to be going from the odd part side to the distinct part side. And so, so this is going to be an odd to distinct. And so the way that I want to describe this is that we want to basically, for all our odd parts, we want to fold them in half. So if that doesn't make sense, well, let me do an example of this. Let's say that we have taken our partitions that we start with is 7 plus 5 plus 3 plus 3. So this is into odd parts. And so for each part successfully, starting with the biggest and going down, we're going to take 7, we're going to, so we kind of think of a line with 7 dots, and then we're going to take it and fold it in half. I guess I'm going to not use dots, I'm going to use boxes instead here, but okay, so we have a line of 7 boxes that now is folded in half right here. And we're going to keep doing this for each one in succession. We're going to take 5, row 5 boxes, bend it in half, stick it here, stick it here, stick it here, so on and so forth. So now the 5. So here's our 7, here's our 5, here's our 3, and then we have one more 3 that sticks on down out there. So if the first job is to draw this picture, and now to give the bijection, we're going to read this picture in a, let me confess, I think the first time you see it's a rather non-intuitive way to read it. But you start in the top right corner. You draw back to the top left corner, and then you draw diagonally down as far as you can go along that main diagonal. So that's a little bit off center there, but that is, we just go down this diagonal. And then we do the same thing. We start, now we just reverse it. We move to the bottom left. We draw up as far as we can. Oh, but we can't draw there. We have to stop when we hit something we've already drawn. And now we draw diagonally down as far as we can go. And we keep doing this. So now we're back to the top right. Draw here to here. And bottom left is here. And we put dots everywhere. Now our job is just to read off how many dots are in each of these little shapes that we drew. So almost kind of looks 7s if you tilt them in the right way. So 1, 2, 3, 4, 5, 6, 7 is the first one. Then we have 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3, 4. And then we have a 1 here. And so 7 plus 5 plus 3 plus 3 gets mapped to 7 plus 6 plus 4 plus 1. That's an example of this map that Sylvester came up with. Any questions so far? Maybe now is a good time just to do a little bit of historical note here. So this is Sylvester. This was he did this work during his time at Johns Hopkins. He was the first math professor, correct, at Johns Hopkins, I believe. Yes, and he had a lot of graduate students. Franklin was working on partitions with him, and this bijection first appeared in a paper with a rather remarkable title, A Constructive Theory of Partitions Arranged in 3 Acts and Interact in an Exodian. And the language in this paper is but let's just say that they don't write math papers like this anymore. This is very highly recommended reading if you want to see Sylvester quoting from Shakespeare in the middle of a math paper. His experience unlike any other paper that
he also wrote before Sylvester. He was unique.
Yes. So Sylvester was a very, very special mathematician. So, okay, so back to this bijection. this bijection ends up preserving, as I said, the reason I care about this bijection in the context of what we're coming up with, it does certain things. And the things that it does, well, so this is just two things that are just purely coincidental here. It happened to preserve the number of parts, that won't always happen. It happened to preserve the largest part, that won't always happen. But there is one thing that it does preserve here. And so it does preserve the following thing. So a nice feature of Sylvester and his bijection is, here's some notation that is very much non-standard. I just came up with it. So let capital lambda 1 be the sum of, here my lowercase lambdas are representing the individual parts in the partition. Lambda 1 is the largest, and we go down. So let lambda 1 be the sum of all the odd index parts. Let capital lambda 2 be the sum of all of the even index parts. And then capital lambda 1 minus capital lambda 2 is equal to the number of parts in the original partition before we did the bijection. And so in this example, so lambda 1 is equal to 7 plus 4 is 11. Lambda 2 is 6 plus 1, which is equal to 7. 11 minus 7 is 4. And that, indeed, there were 4 parts in the original partition. Now, the easy way to kind of see this is that why this has happened. We can actually see that from the picture. Because everything, the parts, so here's lambda 1, here's lambda 2, here's lambda 3, here's lambda 4, and we keep putting 5 and 6, and so on and so forth. So all of the odd index ones are above the main diagonal. All the even index ones are below the main diagonal, but then the main diagonal belongs to the odd index ones. And so how many boxes are there on the main diagonal? 1 for every part in the original partition. And so this is the nice feature that we're going to be exploiting later on in our proof, that there will be a key step in which we very much will care about that. Any questions right now? Okay, so far, I guess, first thing accomplished, our first job is talk about Sylvester. Now we're going to talk about Major MacMahon. So his partition identity, he did a lot of things, and he was very much an experimentalist at heart. He famously verified the Rajarajan identities up to 89 terms and concluded, it must be true, but even if he didn't know how to prove it right away. So a very, very good pre-computer experimentalist.
He was a computer experimentalist, and he was a computer at the same time.
Yes. MacMahon was fabulous at being able to do mental arithmetic very, very quickly. Probably one of the best, if not the best in England at the time. So MacMahon's identity is the following. So it says that the number of partitions into parts congruent to 0, 2, 3, or 4 mod 6 is equal to, and of course for number of partitions, maybe I should have an N here, is equal to the number of partitions of N with no ones. So you can use, in this bunch, so the top part is clearly, in this bunch you can use any numbers you want. You can use them as many times as you want, except you're just not allowed to use 1. And then we can also, there's a third way that we can think about this, and this is that this is also equal to the number of partitions of N where no part appears exactly once. And so going from here to either one of these, this is the main part of the theorem. Going from this one to this one is a little easy exercise we're about to do, because this basically just comes from taking the conjugate of a partition. We draw out and we look at it instead of reading it, by rows, we read it by columns. Then these two things are going to correspond to each other. So here is so here is 3 plus 2. If we can read this as 3 plus 2. So there's no 1s here. If we, let's see, no part appears exactly, what is the largest part does not appear exactly? No, what has gone wrong here?
That second one's supposed to be no ones, or is it?
No part appears
exactly at once.
No.
Oh, sorry. So this no ones is only a part of something else. Yes. I forgot the most important thing here. Not a good thing to do on the deal, but who cares? Because we can patch this up. Hey, we can always check our work. I'm teaching classes. I make lots of mistakes in class. The important thing to do is to realize when something has gone wrong. So that is an important thing. So something has gone wrong. What was the thing that I completely forgot? Not only can we not have any ones, but you can't also have you can't have any 2 consecutive parts. So 3 plus 2 is very much not allowed under this. Let's patch this up to a 4 plus 2, and now this goes away with a 2 plus 2 plus 1 plus 1. And we can see then, this is great because I was about to do a counter example to this, where we could see, because we did have the consecutive part that did result in the 1 occurring. And so this is the way, the no consecutive parts is maybe like the more natural feeling way for me to think about it. But as it turns out, this third way to express it is the most useful for when we actually want to prove things with it.
But you can have repetitions, that's no.
Yeah, and then so Doran brings up a very good point here, which is that one very important difference. If you ever heard me talk about partition identities before, I usually start off talking about Ramanujan identities, other things like that. And also in Euler is that we often say it's like, you're not allowed to repeat any parts, or maybe you can only have every part appear at most twice or 3 times or something like that. MacMahon does not have any condition like that whatsoever. So you can put in you can have as many 5s as you want. You can have 1,000,000 5s. That is completely fine to have in your partition. The thing that you're just not allowed to have is any consecutive parts. Okay, so questions, comments right now. So yeah, please, Brooke.
The first one, could you clarify the number of partitions of n into parts congruent to
So the only numbers that you're allowed to use are stuff that's congruent to 2s, 3s, 4s, and 0s mod 6s. So you can have it. So you can use 2s, you can use 3s, you can use 4s, you can use 6s, you can use 8s, 9s, so on and so forth. You can have those occur as many times as you want. You just can't use 1s and 5s and 7s. So that's very similar in spirit to the odd partitions over here. So here this is saying you're only allowed to use odd numbers. That one is saying you're only allowed to use numbers in these residue classes mod 6.
So for 4, there's 2 of them?
So sorry, say it again.
So for your case of 4, is there 2?
Yeah, let's check this. So we can't use, so 4 certainly works in that. 3 plus 1, okay, we can't use a 1, so that's gone. 2 plus 2, that works. When we can't use a 1, so those 2 are gone. So
okay, so 2 should then be the same as the number of partitions of n with no 1s and non-consecutive parts.
Okay, so and then 4 and 2 plus 2 are again no 1s and no consecutive parts. And then no pair appears exactly once is going to be 2 plus 3 and the all 4s. I'm sorry, that is the 4 ones.
Okay.
So thanks for suggesting that. That was good that we can that we can verify that we know what's going on here. Any other questions or comments right now? Okay, so next thing on our agenda is again, have to touch on the experimentation side of this. So this is I'm going to start talking about a family of partition identities that it was originally conjectured by computer experimentation, project I was working on together with Shashank Kanade and Deb Nandi. And so there's a whole family of them. If I have time today, I'll just write down the general family. I'm going to just work on everything in just one particular example, and hopefully, the infinite family will kind of be clear what's going on. And so through computer experimentation, we managed to conjecture the following identity, and then this provides, the rest of the talk will be bijective proof of this. So, new identity. So, the number of partitions of n into parts congruent to 0, 2, 4, and 5 mod 6. And this is also equal to the number of partitions of n with the following property, that odd parts cannot be exactly 1 or exactly 3 greater than the even part. And just like we had up there, we had a no ones condition. We also have and no ones and no threes. And then we also have, this is by going to a conjugation. So let me just pause right now. So the number of partitions in parts congruent 0, 2, 4, 5. That should feel like the original MacMahon. Number of partitions, and with odd parts cannot be exactly 1 or exactly 3 greater than the even part. That was inspired by the middle condition, like the experimentation. So there, you can't have any part 1 greater than a different part. Here is we're treating the odds and the even separately. So you can't have, for example, 7 plus 6. The odd would be 1 greater than the even. You can't have 7 plus 4. The odd would be 3 greater than even. But you can have, something like 8 plus 7. There's nothing here that says the even can't be the bigger one. And then similarly, we can conjugate this. The number of partitions of n with the following property. A part can appear exactly once or exactly thrice only if there is an even number of parts greater than it. Yeah, that one's ain't moving. Okay.
Matthew, how many times?
I'm teaching in these lecture halls this semester that have that one that can move on me, so I've been spoiled. Okay, so again, I'm not going to justify, but this is again just going by conjugations. That if you think about this these partitions, say, oh, okay, if we conjugate, it ends up with this property. So you can only have a part appear exactly 1 times or exactly 3 times if there's an even number of parts bigger than it. So it can appear exactly twice, that's no problem, or it can appear exactly 4, 5, 6 times, however many times bigger than that, that's no problem either. Okay, questions, comments right now?
So this is new as far as you know?
This is new as far as I know.
Do you ask the experts?
We have been doing some circulation and nothing as in any event one can never be absolutely sure, but I suspect that this and really and the entire family are in fact new. So yeah, please, John.
Do we know whether the number of these partitions is always bigger or smaller than the number of the MacMahon?
This feels like that, because if we're just looking at the product side, well, different. We have a 3 mod 6 versus a 5 mod 6. It feels like that. Eventually the 3 mod 6s should be should win out over the 5 mod 6s. There might be some weird cases early on, but eventually that should happen. I would suspect. Okay, anything else? Okay, so here is going to be the, I don't need this. Everybody's staying on the side of the room, so don't need this anymore. So, so we're going to now come up with, I'll describe the bijection. And again, I'll describe in a bijection of going from something that's written like this to something that's written like this. So, from the 0 to 4, 5 mod 6 to the conjugates. Let me say here, these are the conjugates. And so, 0, 2, 4, 5 mod 6. This is not the right way to think about it. This is really evens or 5 mod 6. That is the right way to think about this. And so this is actually inspired by, at least partially inspired by reading Fu and Sellers recently, within the past 5 years or so, offered a new bijective proof of MacMahon's identity, along with infinite families based off of MacMahon's identity, where they did a similar trick, where they basically read it as evens or 3 mod 6. So this is inspired by that trick. And so the way that we're going to describe a partition is, well, first we're going to say what happens to the even parts. And the most obvious thing to do with even parts is break them in half. So in your partition that has part 0, 2, 4, 5 mod 6, anything even, just replace the even part with 2 copies of whatever m over 2 is. Note that this is not an iterative process. Sometimes in these type of proofs, you keep doing that until you get down to just odd parts. Like if you were to have something like 12 here, that would be allowed. You send it to 6 plus 6. You don't go all the way down to 3 plus 3 plus 3 plus 3. And so then, so that feels like the thing that we should be. And so that should be doing. And so then the big question is what to do with the odd parts. And the odd parts are all of the form 6m sub m sub I minus 1 for some m sub I, because they're congruent to they are congruent to 5 mod 6. And so this was the trickiest part of the proof. I was basically working under the assumption that the even parts have to divide in half in order for the proof to work out. And then the question was, well, what do the odd parts get sent to? And it was basically, I was again kind of working on under the assumption that the even parts and the odd parts would behave differently. That these two maps would be done completely separately from each other. And so I managed to, again, I have to note where the experimentation in this talk is coming in.